Projective geometry is a topic of mathematics. It is the study of geometric properties that are invariant with respect to projective transformations. This means that, compared to elementary geometry, projective geometry has a different setting, projective space, and a selective set of basic geometric concepts. The basic intuitions are that projective space has more points than Euclidean space, for a given dimension, and that geometric transformations are permitted that transform the extra points, called points at infinity, to Euclidean points, and vice versa. Properties meaningful for projective geometry are respected by this new idea of transformation, which is more radical in its effects than expressible by a transformation matrix and translations, the affine transformations. The first issue for geometers is what kind of geometry is adequate for a novel situation. It is not possible to refer to angles in projective geometry as it is in Euclidean geometry, because angle is an example of a concept not invariant with respect to projective transformations, as is seen in perspective drawing. One source for projective geometry was indeed the theory of perspective. Another difference from elementary geometry is the way in which parallel lines can be said to meet in a point at infinity, once the concept is translated into projective geometry's terms. Again, this notion has an intuitive basis, such as railway tracks meeting at the horizon in a perspective drawing. See projective plane for the basics of projective geometry in 2 dimensions. While the ideas were available earlier, projective geometry was mainly a development of the 19th century. This included the theory of complex projective space, the coordinates used, homogeneous coordinates, being complex numbers. Several major types of more abstract mathematics, including invariant theory, the Italian school of algebraic geometry, and Felix Klein's Erlangen program resulting in the study of the classical groups, were based on projective geometry. It was also a subject with a large number of practitioners for its own sake, as synthetic geometry. Another topic that developed from axiomatic studies of projective geometry is finite geometry. The topic of projective geometry is itself now divided into many research subtopics, 2 examples of which are projective algebraic geometry, the study of projective varieties, and projective differential geometry, the study of differential invariants of the projective transformations. Overview: Projective geometry is an elementary non-metrical form of geometry, meaning that it is not based on a concept of distance. In 2 dimensions, it begins with the study of configurations of points and lines. That there is indeed some geometric interest in this sparse setting was seen as projective geometry was developed by Desargues and others in the exploration of the principles of perspective art. In higher dimensional spaces there are considered hyperplanes, that always meet, and other linear subspaces, which exhibit the principle of duality. The simplest illustration of duality is in the projective plane, where the statements 2 distinct points determine a unique line, that is the line through them, and 2 distinct lines determine a unique point, that is their point of intersection, show the same structure as propositions. Projective geometry can also be seen as a geometry of constructions with a straight edge alone. Since projective geometry excludes compass constructions, there are no circles, no angles, no measurements, no parallels, and no concept of intermediacy. It was realized that the theorems that do apply to projective geometry are simpler statements. For example, the different conic sections are all equivalent in complex projective geometry, and some theorems about circles can be considered as special cases of these general theorems. During the early 19th century, the work of Jean-Victor Poncelet, Lazare Carnot and others established projective geometry as an independent field of mathematics. Its rigorous foundations were addressed by Carl von Staudt and perfected by Italians Giuseppe Pino, Mario Piri, Alessandro Padua and Gino Fano during the late 19th century. Projective geometry, like affine and Euclidean geometry, could also be developed from the Erlangen program of Felix Klein. Projective geometry is characterized by invariants under transformations of the projective group. After much work on the very large number of theorems in this subject, therefore, the basics of projective geometry became understood. The incidence structure and the cross ratio are fundamental invariants under projective transformations. Projective geometry can be modeled by the affine plane, or affine space, plus a line, hyperplane, at infinity and then treating that line, or hyperplane, as ordinary. An algebraic model for doing projective geometry in the style of analytic geometry is given by homogeneous coordinates. On the other hand, axiomatic studies revealed the existence of non-disargument planes, examples to show that the axioms of incidence can be modeled, in two dimensions only, by structures not accessible to reasoning through homogeneous coordinate systems. In a foundational sense, projective geometry and ordered geometry are elementary since they involve a minimum of axioms and either can be used as the foundation for affine and Euclidean geometry. Projective geometry is not ordered and so it is a distinct foundation for geometry. History. The first geometrical properties of a projective nature were discovered during the 3rd century by Pappus of Alexandria. Filippo Brunelleschi, 1404–1472, started investigating the geometry of perspective during 1425. See the history of perspective for a more thorough discussion of the work in the fine arts that motivated much of the development of projective geometry. Johannes Kepler, 1571–1630, and Gerard Desargues, 1591–1661, independently developed the concept of the point at infinity. Desargues developed an alternative way of constructing perspective drawings by generalizing the use of vanishing points to include the case when these are infinitely far away. He made Euclidean geometry, where parallel lines are truly parallel, into a special case of an all-encompassing geometric system. Desargues' study on conic sections drew the attention of 16-year-old Blaise Pascal and helped him formulate Pascal's theorem. The works of Gaspard Monge at the end of 18th and beginning of 19th century were important for the subsequent development of projective geometry. The work of Desargues was ignored until Michel Chisels chanced upon a handwritten copy during 1845. Meanwhile, Jean-Victor Poncelet had published the foundational treatise on projective geometry during 1822. Poncelet separated the projective properties of objects in individual class and establishing a relationship between metric and projective properties. The non-Euclidean geometries discovered soon thereafter were eventually demonstrated to have models, such as the Klein model of hyperbolic space, relating to projective geometry. This early 19th century projective geometry was intermediate from analytic geometry to algebraic geometry. When treated in terms of homogeneous coordinates, projective geometry seems like an extension or technical improvement of the use of coordinates to reduce geometric problems to algebra, an extension reducing the number of special cases. The detailed study of quadrics and the line geometry of Julius Plucker still form a rich set of examples for geometers working with more general concepts. The work of Poncelet, Jacob Steiner and others was not intended to extend analytic geometry. Techniques were supposed to be synthetic, In effect, projective space as now understood was to be introduced axiomatically. As a result, reformulating early work in projective geometry so that it satisfies current standards of rigor can be somewhat difficult. Even in the case of the projective plane alone, the axiomatic approach can result in models not describable via linear algebra. This period in geometry was overtaken by research on the general algebraic curve by Glebs, Riemann, Max Noether and others, which stretched existing techniques, and then by invariant theory. Towards the end of the century, the Italian school of algebraic geometry, Enriques, Segur, Severi, broke out of the traditional subject matter into an area demanding deeper techniques. During the later part of the 19th century, the detailed study of projective geometry became less fashionable, although the literature is voluminous. Some important work was done in enumerative geometry in particular, by Schubert, that is now considered as anticipating the theory of Turing classes, taken as representing the algebraic topology of Grassmannians. Paul Dirac studied projective geometry and used it as a basis for developing his concepts of quantum mechanics, although his published results were always in algebraic form. See a blog article referring to an article in a book on this subject, also to a talk Dirac gave to a general audience during 1972 in Boston about projective geometry, without specifics as to its application in his physics.